Miss Jody here again with another video for our Matter and Energy class that usually meets on Thursdays, 9:30 to noon. So as we're going along, just as a reminder, we're still trying to finish up our journals during this separation time. So I would like for you to still be trying to take notes on a half sheet of paper and put the title of the notes on the back so that when we get back together, I can glue them right into your journal so that we don't have all these empty pages in our journal. I'm going to keep the journals going, but I want to try to be able to get some stuff done during our separation time. That way when we come back together, we can do some of our experiments. All right, so our last video, we were continuing on the idea of waves. And so remember we talked about, let me flip back here, the terminology of waves, and then the wave characteristics. And remember with waves, there were four main things we were always looking at: the wavelength, the amplitude, how much it's displaced, the frequency, how frequently it's coming at you or whatnot, or going past a certain point, and the speed of the wave, how fast it's going divided by the distance. And so with waves, I remember I gave you this little thing for you to do with the different colors, and mine turned out really good, and I'm going to put that in my journal that Catherine did for me. And we talked last video about wave behavior. So waves will do certain things. They have a certain behavior about them. There's the process of reflection, refraction, diffraction, and then interference. And so remember we talked about how the waves will behave, and you can kind of track their behavior, and waves will behave a certain way. And so that was leading up for us to then start studying different types of waves. And so we're going to look at the sound waves in this video. And so sound, what is sound? Okay, so sound is vibrations traveling through a medium in the form of longitudinal pressure waves. Now, if you remember the longitudinal, remember we had the transverse waves, and then we had the longitudinal. They were the ones that were more like slinky motion for our own way of visualizing it. So remember there was a compression where it squeezed together, and then a spreading out, which we called a rarefaction, and then squeezed together, and then spread out. And that was that wave-like behavior of the longitudinal pressure waves, the way that the waves would propagate down through the medium. So the sound is this type. So sound's kind of like the slinky wave. It's not the up and down ones where it was the transverse back and forth oscillations. So it's the slinky type ones. So with sound, what we have is we have movement of sound as it goes through the media. It's going in all directions, like a 3D ever expanding bubble. And so it's kind of hard to visualize this because it's hard to visualize sound, but I thought what we'd do is we would see how this sound moves through the media. So that's the idea, that it has something it's traveling through. And you'll see on this point here, sound requires the medium to travel through, but we'll get to that in a minute. But so here's a little picture. This is the half of the sheet of the diagrams, or the PDF I'm sending you that has the two half sheet diagrams on it. And I'm gonna pretend like this little guy here is me, and I'm gonna have all of this. Actually, why don't I do a pink? Let's see if that pink works. Okay, so I'm gonna just draw all these little pink dots. These pink dots are gonna be all the air around me. Okay, now it would take me a long time to draw tons and tons, so I'm only going to do a few so we can get that concept. But you can imagine the air molecules all around you. They're everywhere, and there's so many of them, billions and billions and billions, right, of all these air molecules. And so as I visualize this with the little pink dot, I'm going to switch to another color to illustrate the sound moving in all directions like a bubble as it comes out from the source. Okay, so let's say there was a sound like a scream. Maybe it's coming from me. That would be fine. Let me see if I want to use this purple, or that'd be too much. I'm gonna use like an orange because I got a skinny marker for that. So there's all my air molecules, and then say I make the sound and it begins to come out, and what it's gonna do is it's gonna move. Oops, that almost looks like the pink. Maybe I should switch that here. I don't want that to be looking exactly like the pink. How about I use this blue colored pencil? Maybe that will help. All right, so as it's coming out, it's vibrating these air molecules, and the next vibration then moves to the next one, and I guess I don't have them close enough to show that, and I'd have to do a whole bunch. But just coming out from my head here, I'll do a few just to make it more realistic. Okay, and so as my air molecules all around me are vibrating, then the vibrations are what's moving down. So it's coming in all directions. The sound comes out and it's got its first set of vibrations, and that's that set of vibrations there. And then it goes, the vibration moves to the next air molecule, then to the next air molecule, and let's say there was one there, and the next air molecule, and it just keeps moving out in all directions. And so just shaking and vibrating these air molecules, and then that vibration hits that one, and the energy is transferred to this one, and then the energy is transferred to this one, and it keeps moving out away from the air. And then eventually, I'm going to do it like this and pretend like it was all these air molecules, and they pretend like I had the little vibrations on each of them. Then as it moves out, and I'd have to have a whole bunch, I would have had done a better job with my drawing, right? And when you're doing this, you can definitely do a better job of your drawing, putting a whole bunch of those dots in there. And so the sound begins to move out in all directions in this vibration, each one of these vibrations passing on to the next air molecule and the next air molecule and the next air molecule. And again, you'd have to do a really good job of dotting your air molecules all around your little guy, way better than what I did. And then draw all of your little vibrations around the air molecules as the vibrations pass from one molecule to the next molecule to the next molecule to the next molecule. And the sound would just be coming, it would be propagating, moving from vibration to vibration to the next one, to the next one, to the next one, to the next one, creating this wave-like behavior, or pattern, I should say. And so when this says the movement of sound goes in all directions like a 3D ever-expanding bubble, you picture the sound moving out, and of course then eventually it'll lose the energy because it loses a little energy each time with the vibrations. It loses a little bit from the jiggling. A little bit of that is lost in the process of the transfer of the energy. And so eventually we would lose that, but it would just bubble out like a big old bubble. Okay, so that's how sound would be traveling. Now, of course, if we wanted to travel in a certain direction, we could focus it and make like a megaphone. We could create a tunnel that it could go through. And if we created a tunnel, like say for instance, if you roll up this paper and then I'm making the sound go through just this particular tunnel. If I made this small enough down here and I made the sound only be able to go through here, then all of those vibrations will have to get stuck through the tunnel and concentrate there. But if you're just talking about just a sound as it's just in the open air or whatever, it will just move out like that bubble. So the thing is that we have to note is that the air itself is not moving from the source of the sound. So it's not that when this one little air molecule begins to vibrate, this air molecule doesn't end up over here. He doesn't travel through it all. He just vibrates, and the vibration then he knocks into the next guy, and that energy gets transferred to him, and then the energy gets transferred to the next guy, and the next guy, and the next guy. And so it moves through the media, but the air molecule that you started with that was vibrating, he doesn't move over here. So we talked about that before when we illustrated when the water wave was moving and the ducky just kept bouncing up and down. So the air itself is not moving away from the source. And so it's just the vibrations are moving through it. Now, sound does require a medium, meaning it needs something to travel through, and we just saw it traveling through air there with the vibrations. It can travel through many things, many substances, water, different metals. It can travel through things, but it does have to have something to travel through. Where when we get to looking at light, light is thought to not need anything to travel through. And we see it being able to travel through absolute, complete nothingness, which we would call the vacuum. And so this was figured out about sound, the fact that it needs a medium to travel through. In 1660, Robert Boyle, he created an experiment which some call the hanging watch or the hanging alarm or whatever. And so what he did is he set an alarm, and now the alarm isn't like our fancy alarms now. It's kind of like the watches they used to hang from, like on a chain, those types of watches. So he suspended that type of clock watch arm or clock that had an alarm on it, and he suspended it in an airtight glass container, and then he pumped all the air out. And so imagine, this is Robert Boyle here, and I'm just going to draw my little experiment here. I don't know exactly what it looked like. There's a picture in our book on it. I'm not going to draw it perfectly, but you'll get my point here. So I've got this little airtight container, and I'm going to suspend from a string or something. I'm going to put my little clock in there, my little alarm clock. That's dangling from that. And it has a little bell that can be rung with a little hammer on it. And when I set the alarm, and it's a certain time when it's supposed to bing, ding, 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 then it'll be inside this airtight container. So he stuck it in this airtight container, and then he used a vacuum to pump out. And I'm just going to create, I don't know exactly what it looked like where, but you get the point. He's going to use a pump and you can draw yours, however. There is a good picture in the book that will be a better picture than what you see going on here with Miss Jody. And so there was a whole bunch of these air molecules in it, but then through the pump, then all the air molecules were pumped out. And so I'll just put air over here. So all the air was pumped out, so there was nothing, no invisible molecules hanging inside that contraption. And I'm not sure if it was flat. I'm going to set it on a table here, okay? It could have been on something else. But anyways, and this is my pump. And so my pump pumps out all the air. And so then, as it was time for the bell to ring, you could see the hammer was hitting the bell, ding, 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 but no sound was being heard. And this illustrated to Boyle, Robert Boyle, that sound actually had to have that air to travel through. So even though the bell was bing, 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 it was nothing, no sound. And then when he added a little bit of air back into the sealed off container, he would add a little bit, he would start to hear just a little faint sound. And then the more air that he added back in, then the sound came back. And so this helped him understand that there was no sound even though the hammer of the arm was striking the bell. That was because there needed to be some air in there for sound to travel. And now, once he figured that out, then that gave us the idea that sound had to have a medium to travel through in that particular way. So with sound, when we start to look at sound, the next page, and this is 2 note pages today on this one, is then we're going to look at sound characteristics. Now, if you remember back when we were looking at waves, let me flip back here. We looked at wave terminology. We said, okay, what are waves? And then we did a page called wave characteristics, like things that describe waves, and it was always wavelength, amplitude, frequency, speed. Now we're going to do the same thing with sound. We're going to have the same things that characterize sound because it's a wave, right? So wavelength, amplitude, frequency, and speed. So when we look at that, we say, okay, wavelength, that means the length of the wave. Now this wave is the longitudinal wave, so like the slinky, the squeeze together and spread out one. And so it still has the same symbol of wavelength, the lambda there, but we figure out the length of the wave just like we did when we talked about the wave characteristics. So we figure out the length of the wave. Now what we found is with sound, if you have a low frequency wave, that means it's hitting you only a low amount of time. So in like 1 second, the sound wave hits you like once or twice. That's low frequency. So if it's low frequency, then it must have a very long wavelength. So I tried to illustrate, this is a speaker. And so my speaker is got a longer wavelength, longer wavelength, but a lower frequency. And so it would come out and I would have the lower amount, only 3 times it hit me of the sound wave, and that would mean that I would have a longer wavelength, a lot longer wavelength for each one of these. So here would be one wavelength, and that would be the next wavelength. Now, when you would have in my speaker here a high frequency where the sound wave is hitting you many times in that 1 second, then it would mean I would have to have a smaller wavelength to get all of those, like 1, 2, 3, 4, 5, 6, let's say. So this is double the amount that's hitting me on this one. So if I had a higher frequency, then I'm gonna end up having a smaller wavelength. Here's my wavelength there, my next wavelength, wavelength. See, they're not that, they're smaller, the wavelengths, and this is longer wavelengths. So that holds true to the same thing we see in all wave-like behaviors. All right, but what about the next one, amplitude? Now, amplitude is the extent to which the particles are displaced. So you remember when we were talking about the waves that were more like the ones that were like this, the transverse waves. It's kind of easier to see because we were saying, okay, here's that invisible line of the, say, the water. And if the wave is really strong, it will displace it up this much. Say it's a stronger wave, has more amplitude, it displaced it this much. Do you remember that? And so that's that same concept, but we got to remember we're talking about the waves this way, where it's going to be squeezed and then stretched out, and then squeezed and stretched out. And so when we talk about that with the amplitude, it's the same thing. It's just the intensity. And so what happens is with sound, when we're talking about amplitude, we use the word intensity. So if you've ever heard anybody talk about, oh, the intensity of the sound, it's the strength of the sound wave. It's kind of linked to what we call loudness, how loud something is. So it's very intense, these pressure waves. So at the squeezing and then the spreading out, and then squeezing and then the spreading out. What is the extent to which the particles are displaced? So they give you an illustration here, like if you're plucking a guitar. So if you pluck the guitar, you have the string, and it's going to always have the same frequency of vibration. But if you pluck it really, really hard, it might be really loud. If you pluck it really, really light, ding, then you've only displaced it a smaller amount. So think of the string and displacing it a lot, like pulling it really, really hard. And that will create a lot of intensity, a lot more loudness, right? So the amount of energy per unit of time. So for how much energy, really a big pluck or just a little pluck? Okay, so whenever we talk about sound, sometimes you don't hear people say amplitude. You'll hear them say intensity. It's that same category, and you have to remember, that's why I circled this to know that it goes with amplitude. All right, then we got frequency. We can't leave that one out. Frequency is the number of waves that pass a given point per unit of time. So how frequent is it hitting you? How frequent is it coming? And we talk about frequency in cycles. And so if we talk about sound coming at you in cycles, if you see this little chart over here, I put 20 cycles per second, and then I put an arrow to 20,000 cycles per second. So that's the frequencies between 20 to 20,000 cycles per second. That's the frequency that our ears can hear. Now that doesn't mean that sound can't even be more frequent than that or less frequent than that. If it's less frequent and it's coming less than 20 times per second, then it was what we would call infrasonic. And so whenever we have infrasonic, we're going to be looking at that, and you know the sonic the sonic word is going to be the sound. So anytime you're going to add sonic to it, you're going to be talking about the sound side of it. So infrasonic. And then in between 20 to 20,000 is what we can hear. So if you go underneath that infrasonic, we can't hear that. You're going below the audible region of sound for us, for our particular ears. But what if you go above that? You won't be able to hear it because our ears can't pick it up, but we would call it the ultrasonic. Have you ever heard somebody say, oh, that's really ultrasonic? That's really high frequencies of sound, but we can't hear it with our ears, but other organisms have different levels of what they can hear. So now frequency is going to be linked to pitch. So pitch is the effect of frequency on the way the human ear perceives sound. So if you ever heard somebody say, oh, you're so out of pitch, They're saying, they're linking that to the frequency of the sound that's going on. So pitch is part of that frequency world. So again, I circled this because if it's amplitude and we hear somebody say intensity, they're talking about this world. If we hear somebody say pitch, they're talking about this world, the frequency world. All right, and then we don't want to forget speed, because speed is still one of those characteristics of wave. And so sound has speed. Now, speed is the distance divided by time. And so we can calculate the speed of sound. But see, the speed of sound changes in different substances. And so as it's moving through air molecules, like our little picture with the little dots, if it's dry air and if it's at a temperature of 0 degrees Celsius, then it will be moving at approximately 330 meters per second. So that would be the speed of sound in dry air at that temperature. Now, why do I have to put temperature there? Why couldn't I just say dry air? Well, here's the thing. Sound will travel through warmer air faster. So each degree of Celsius that you rise up, the speed will increase 0.6 meters per second. So if I get it warmer, then my sound can travel faster. And that would make sense, right? Because the spreading out of the air molecules, and then the vibration can go from one to the next, and they're not as compact in, right? Sound can also go through other things like water and metal and all that. And I just put water because I think it's pretty cool that water is 4 times, it's faster, 4 times greater than its speed through air. So it's going to travel through water really fast. And with the speed, we also have a chart like we did with frequency. There is SOS, the speed of sound. So the average speed of sound, if you in whatever type of substance you're traveling through, if you are gonna go below the speed of sound, you would be subsonic. If you would go above the speed of sound, you'd be supersonic. So you've heard those words, right? Infrasonic, ultrasonic, subsonic, supersonic. They go with these two particular categories. Now, the diagram page that I sent you also has this chart that's going to go in our journals on the half sheet. And so this is a chart for you just to look at. This is the level of our where our ears can hear certain things. And the problem with where our ears can hear certain things is if we get it too loud. Now, this is all linked to the intensity, the amplitude of the sound wave. If we get it too loud, it's not going to be good for us. And so when we look at this scale, we can see, okay, just like leaves rustling, that's about a 20. Now, when I was talking about audible sound over here from 20 cycles to 20,000 cycles, that's not really what this number means. This number is what we call the decibel scale. And this was created so that we could figure out the intensity of the sound, and as it moved up, it's multiplied by another set of intensity. So this 0, 10, 20, 30, 40, 50 is not the same as the cycles per second that we looked at with frequency. This is all about the intensity. And this decibel scale, and you can look in your book, it'll explain a little bit more on that. We want to see that at a certain point, it's going to start being trouble if we are in the presence of too much sound. So you see on the side, it says no risk, negligible risk, and then at this level up here, it's at risk. And what do you see? The iPod in there with the little earphones, because if we allow too much sound, especially on our earphones, going directly into the sensor organ that's supposed to help us with sound, we're going to be causing it some trouble. So I want you to look at this real well, and I want you to kind of know where these things are. And if we have prolonged sound exposure in the higher regions, we're going to be damaging our ears, okay? Now with this diagram, there's not a lot to do on it, but you could color these pictures for me, and then that way when we glue it in, it'd be looking nice in our journal, okay? All right, so that's it for this lesson on sound and its characteristics, and I will see you in the next one.